next we're going to talk about the chain rule. Now, we've taken a lot of derivatives. We have that document with 22 derivative laws. But there are many, many functions those laws don't take care of. For example, how do you take the derivative of sine of 3x? Well, we don't know how to do that with those laws. How do we take the derivative of e to the x squared plus 2? Well, we don't know how to do those with those laws. We only know with those laws what happens if, in this case, the inside of that function is just an x. Or in this case, if the exponent is just an x. But this next rule we cover, called the chain rule, is going to show us how we can take those derivatives. I'm going to give two notations for the chain rule. First notation, the derivative of a composition of functions, f of g of x. So those two examples I erased could be broken down as a composition, because it's sine of 3x, e to the x squared plus 2. And the chain rule tells us how to take derivatives of a composition. F prime of g of x times g prime of x. Well, that's one notation for the chain rule. We will use that a couple times. A more common notation that we'll use, I'll just call it alternative notation, for the chain rule is that dy dx equals dy du times du dx. So that's times in the middle there. One of the reasons this notation is nice is because we can sometimes use behavior of fractions to understand derivatives. Now, this derivative notation is not a fraction. Right here, in using chain rule, we can see how thinking of it as a fraction is going to help us to find a derivative. Again, not a fraction. This is not a fraction. The chain rule in Calc 3, for example, looks like this, except this type of thing shows up twice. And in that case, you'd get dy dx equals dy dx plus dy dx. 1 equals 2, which is not true. So it's not a fraction, but we can use conveniences of fractional notation to find the derivative using chain rule. Now, in this second notation, we have y's and x's, but there's also a u in there. So to use that notation, you would have to figure out what a convenient choice of u is. And in all the examples we'll do, the choice of u would be a substitution, which brings you back to the 22 derivative rules listed in the document on derivative rules. But let's do several examples. Let's just start with those first two I wrote. A, f of x, so directions find, f prime of x. F of x equals sine of 3x. B, so in the first one I'm going to use the first notation, I guess, and in the second one I'll use the second notation. So A, f x equals sine of 3x. B, y equals x squared plus 2. So find f prime of x or dy dx. I can sit down here. So here, in the first one, we would need to choose two functions. And there are some ways you could write this. I'm going to write it like this. That inside piece of the function, 3x, is going to be our g of x. So f prime of x, well, maybe I'll just write it like this, equals sine of g of x. So f of x is sine of g of x. Well, in this case, f is sine. What's f prime? F is sine. What's f prime? Derivative of sine is cosine. What's on the inside? Well, this tells us to leave g of x on the inside. Leave g of x on the inside. G of x is 3x. But then you have to multiply by g prime of x. What's g prime of x? Well, g of x is 3x, derivative of 3x is 3. So we get 3 cosine of 3x. So we have the derivative of sine of 3x is cosine, leave the inside alone, but then multiply by the derivative of the inside. When doing chain rule problems, I very commonly like to think of it as an outside and an inside function, where you do the derivative by doing the derivative of the outside, leave the inside alone, then multiply by the derivative of the inside. Derivative of sine is cosine, leave 3x alone, multiply by the derivative of 3x. And you get 3 cosine of 3x. So that's with our first notation. How about with the second notation? Well, we'll use the second notation down here for e to the x squared plus 2. Well, we don't have a rule for e to the x squared plus 2, but we do have a rule for e to a single variable, e to the x, for example, or in this case, e to the u. So what we're going to do, where am I going to write this? Let's write it here. We're going to make a substitution in that exponent. And what happens if we do that? Well, if you do that, well, first what happens is the original function is now e to the u. What else happens? Well, now we can find these two pieces. We can find dy du. We can find du dx. So I'm just going to keep going over here. So, and so, 2 lines. So dy du. What's dy du? Well, y is e to the x squared plus 2. Y is e to the u. Derivative of e to the u is itself. And how about du dx? U is now a function of x. Well, y up here is now a function of u. So du dx, 2x plus 0. So just 2x. Well, we're not done. We need dy dx. And a convenience of this Leibniz fractional notation is that it looks like we could just multiply these and get dy dx, and in fact, we can. So let's make our concluding sentence. So, dy dx equals dy du dx. What's dy du? Dy du is e to the u. So let's write u. So dy du is e to the u. What's du dx? It's 2x. And now, we want our answer in terms of x. We just have to get rid of that u. We can use that substitution. And I'm also going to put 2x in front. So either notation you can use. When I first learned this, I preferred the u substitution method. So let's do a bunch more examples. Well, yeah, let's do a bunch more examples. Okay. Example. Find dy dx. A. And in some of these I will go through the u substitution, and some of them I won't. I'm going to need a y if I'm going to say dy dx. Y equals 7x minus 4x cubed all to the 5th. B. Y equals tangent of 5x squared plus 3x negative 2. C. Y equals tangent x plus cosine x all to the negative 4. D. Y equals let's do it like this. Secant of 5x e. Y equals tangent of 3x. Now, I've been using tangent a lot. Let's do something else. Let's do cotangent. So y equals, let's do secant of 5x cotangent of 3x. And then we'll do a few more after this. But for now, let's just do these. I'm just making sure I hit record at the beginning of this. You don't want to do one of these and forget to hit record halfway through. So let's do these, but before doing these, I'm going to erase most of this work over here and just look at question and answer for these first two. Because as you do a bunch of these, you start noticing some patterns. Start with sine of x. Derivative is cosine of the inside times derivative of the inside. Derivative of sine is cosine multiplied by derivative of the inside. Derivative of e to the x is itself. But then you multiply by the derivative of that exponent, which is 2x. So all of these chain rule examples will work in a similar way, where you take the derivative as you normally would, but then you multiply by the derivative of, in this case, the exponent. In this case, the inside function. So let's do that with some of these examples. This pen's already got, so I'll use this other one. Oh, it's a marker, not a pen. Part A. Well, there's no algebraic derivative rule which tells us how we can take the derivative up here. We have 7x minus 4x cubed all to the fifth. But we do know how to take the derivative of just x to the fifth. So up here, let's let u be 7x minus 4x cubed. Well, what happens if we let u be 7x minus 4x cubed? Well, then y is just u to the fifth. Great. Now we can take a du dx, 7 minus 12x squared, and we can take a dy du. That's a u. Y is u to the fifth, so dy du is 5u to the fourth. Well then, dy dx is dy du times du dx, which is what? 5u to the fourth times 7 minus 12x squared. And we don't want u's in our answer, so we need 5, what's u? 7x minus 4x cubed to the fourth times 7 minus 12x squared. So we let u be our inside quantity here, and then we were able to take these two derivatives, dy du, du dx, using the algebraic derivative rules. And that is what we want our substitution to do. We want it to turn what we have into, in this case, two algebraic derivative rules. Then we combine them by multiplying, and then get rid of u. B. Well, we have tangent of something. We know how to take derivative of tangent of x. So let's let u be this something. (5x squared plus 3x to the negative 2). Well, what happens if we do that? Well, then y is just tangent of u. Well, we can take both of these derivatives using those 4 pages of rules. So du dx is what? 10x minus 6x negative 3, not negative 1. dy du is secant squared of u. Well, now we just combine those two, multiply those two to get our answer and get rid of the u. So dy dx is dy du, secant squared of u, times du dx, so times 10x minus 6x to the negative 3. So multiply those two answers, and now get rid of u with that substitution there. So it's secant squared of 5x squared plus 3x to the negative 2, all times 10x minus 6x to the negative 3. So we had a tangent function, and its derivative was a secant squared function. But then we multiplied by the derivative of that inside function. And in this first one, we had a function to the fifth. And look at our answer. We had a function to the fifth. The derivative was 5 of them to the fourth. Well, we knew that derivative of x to the fifth was 5x to the fourth. But here we're putting more than just an x there. And we still have 5 of them to the fourth. But then you need to multiply by derivative of the inside function. So let's use that observation for problem 3 and do it without a substitution. In the first one, we had a function to the fifth. Derivative was 5 of them to the fourth. Here we have problem 3, problem C. Here we have a function to the negative fourth. So the derivative is going to be negative 4 of them to the negative fifth. But then you need to use chain rule. So we have negative 4 of them. What is it? Tangent plus cosine. All to the negative fifth. We have a function to the negative fourth. Derivative would be negative 4 of them to the negative fifth. But then you use chain rule. So times derivative of the inside. Derivative of the inside, we do them one at a time. Derivative of tangent is secant squared. Derivative of cosine is negative sine. So this answer for C should look very similar to the answer for A. That's why I left the answer for A up here. Not just because of the 4 and the 5, because of the power rule and the chain rule. If you wanted, for part C, if you wanted to use substitution, u would be tangent x plus cosine of x. How about D? Well, D we have secant of 5x. Let's go through a u substitution here. We know how to take derivative of secant x, so let's let u equal 5x, so that y equals secant of u. Well, we can take these derivatives now. So du dx is 5, dy du is secant of u times tangent of u. Well, now dy dx is given by their product. So dy dx is given by their product. So 5 secant of u, I'm going to get rid of u in this step, 5 secant of 5x tangent of u, so tangent of 5x. So derivative of secant is secant u tangent u. Du dx is 5. So use the chain rule to get these pieces, multiply them together. So you get 5 secant u tangent u, u equals 5x. Notice there's only one 5 here in front. But maybe I shouldn't have erased part D here. Notice how we took that derivative. Derivative of secant is secant tangent. Then you multiply by the derivative of 5. Well, down here, we're kind of combining them. We now have secant of 5x times cotangent of 3x. So we're going to need, first, a product rule, and we'll see what happens from there. So let's do that up here. Part E. dy dx equals, well, it's a product rule. Derivative of secant 5x, well, we just found that down here. So 5 secant of 5x tangent of 5x times the second times cotangent of 3x. So we have derivative of the first times the second plus first derivative of the second. What's the derivative of cotangent of 3x? Well, we can do a similar argument to part D. Let u equal 3x and so on. Or we could use our shortcut observation. Derivative of cotangent is negative cosecant squared. So we have negative cosecant squared. There's cosecant squared. There's negative. So derivative of cotangent is negative cosecant squared, but then multiplied by the derivative of the inside, which in this case is 3. So we have derivative of the first times the second plus the first times the derivative of the second. So if you wanted the u substitution for the second derivative taken there, it would be u equals 3x. And the argument would be similar to the argument for part D. So let's do a couple more. Let's see, what do I have over here? Maybe I should have written this afterwards. F. Let's do, what was it, secant y equals secant of 5x cotangent of 3x again, but here we're going to raise it all to the 43rd power. G. Y equals root x squared plus 3x. Let's see, what else do we have? I'm going to do that one. Do I want to do that one next? No. Yeah, okay, sure. H, y equals the inverse tangent of, I don't need the parentheses, of root x squared plus 3x. And let's do an I. I would be, how about, did all those? Y equals cosine to the 4th of x, and let's do a j. J would be, we didn't do a log yet, did we? No. Do I have one with a log? I definitely should. Yeah, let's do y equals natural log of, let's do 3x squared plus 7x plus 5, I guess. That one's good. And we will do a k after this. There's one other type I would like to see. Let's do a k and an L after this. So I'm just going to write myself a note up here, K and L. So I don't have to go back there. Would be something like that. And L would be a something like that. Okay, let's start with f. Well, we have secant 5x cotangent 3x all to the 43rd. Well, in part E, we did the derivative of the inside. But here we have a function to the 43rd power. Derivative of something to the 43rd is 43 of them to the 42nd. But then you multiply by derivative of the inside. So I'm just going to say it like this. Times star, where star is the answer to part E. That's an O. To part E. So we have a function to the, we have part E all to the 43rd. So the derivative is going to be 43 of them to the 42nd times the derivative of the inside, which was given in part E. Part G. Well, part G, we have y equals root x squared plus 3x. So we have something to the 1/2. Let's do a u substitution here. Because we know how to take derivative of something to the 1/2. So if we let u be that something, then y is u to the 1/2. And now we can do dy du, du dx. I'm going to erase this so it's out of the way. So du dx, 2x plus 3, dy du is what? Well, it's u to the 1/2, so it's a half u to the half minus 1, so half u to the negative half. Well, then we can find dy dx. Just multiply these together. So we get a half of u to the negative half times 2x plus 3. And we just need to get rid of u now, so we have half of x squared plus 3x to the negative half times 2x plus 3. And you can leave your answer like that. As the semester goes, we will see that we want to simplify some of the, well, we'll see that we want to write some of these with square roots as their fraction form. So I'm just going to write this as the fraction. 2x plus 3 all over 2, from that 2, times root x squared, it's a lousy root, 2 root x squared plus 3x. So you could use the remark at the end of lecture 4 point, what week is that? And that was 5.1. Yeah, 5.1 on square root functions. You get 1 over 2 root x times the derivative of that inside. So let's do the next one now. Well, we have inverse tangent of something. We know how to take the derivative of the inverse tangent function. But we don't know how to take inverse tangent of something more than x just yet. Well, we do with chain rule. But let's do the substitution. Let u be the inside so that y equals the inverse tangent of u. Well, now we can do our chain rule. So dy dx equals dy du du dx. What's dy du? Dy du, derivative of tangent inverse, is 1 over 1 plus u squared. What's du dx? Right here. We did that in part G. So we made our u substitution. dy du, derivative of tangent inverse u is 1 over 1 plus u squared, times du dx. Du dx, derivative of that we did in part G. And now we just want to get rid of u. What is u? U is root x squared plus 3x. So this equals what? 1 over 1 plus x squared plus 3x times 2x plus 3 over 2 root x squared plus 3x. 1 over 1 plus u squared. Notice u squared is the square root squared, so that just equaled 1 or x squared plus 3x. You don't have to write that as one fraction. That's okay the way it's written. So I, j, k, I'll put up here. What do I want for k? Let's do sine of, let's just do sine and cosine. Sine of cosine of 4x and L. Y equals 7 to the x squared minus 3x. Okay. So now let's do I. So I, what do we have? We have cosine to the fourth. What is cosine to the fourth? Well, it's cosine to the fourth. It's cosine x all to the fourth. How do we take the derivative of a function to the fourth? Well, we do 4 of them cubed. And then we multiply by the derivative of the inside. Derivative of the inside, derivative of cosine, is negative sine. If you want, you could rewrite this, negative 4 cosine cubed of x, sine of x like that. It looks a little nicer. But this function in I is a function to the fourth power. If you wanted a u substitution, u would be cosine of x. J, log of something. How do we do log of something? Well, let's write out the u substitution. This part J will show up several times, something like this. So I'll go through it in detail. So we know how to take derivative of log of x. So if there's more than an x on the inside, derivative would be, so if there's more than x, we'll use a u substitution to get rid of that. So u equals 3x squared plus 7x plus 5. Then y equals log of u, natural log. Well, what's du dx? And what's dy du? Derivative of u with respect to x would be what? 6x plus 7. What's dy du? Well, it's log of u. Derivative of log x is 1 over x, so derivative of log u is 1 over u. Well, now, what's dy dx? So, dy dx equals this times that. Let's write that out. 1 over u times 6x plus 7. Well, let's get rid of u. So it equals 1 over 3x squared plus 7x plus 5 times 6x plus 7. And let's just write that as one fraction. We will see for a couple topics that writing this as one fraction will help us. That's an equal sign. As one fraction, it's 6x plus 7 over 3x squared plus 7x plus 5. So we have all those details. Let's just look at the question and the answer now. So we have log of something. Derivative of log of something is 1 over that thing. But then chain rule says to multiply by the derivative of that thing. So we have 1 over that thing times the derivative. That can always be rewritten as this fraction. Derivative of the inside over the inside. It's a very convenient shortcut that we'll see a couple times for a couple applications. I'm just debating if I want to do another example. Let's not do another example like that. Let's just do k and l. So derivative of log of something, derivative of that thing over itself. K. What do we have for k? Sine of cosine of 4x. Sine of cosine of 4x. Well, it's a sine function. What's it the sine of? It's the sine of the cosine of 4x. Well, okay, we let u equal this inside piece, so then y is just sine of u. So what's dy dx? Well, it's dy du, which is cosine of u, times du dx. What's du dx? Well, dy du is cosine of u, du dx. Well, to find du dx, we would need another chain rule. Because derivative of cosine of 4x, well, we would need to use a substitution to get rid of that 4x. You can let a different u be 4x here. But derivative of cosine of 4x, well, it's a cosine function. Derivative is a negative sine of 4x times the derivative of 4x, which is 4. So we get negative 4 sine of 4x. So negative 4 sine of 4x. And I'm just going to reorganize this and get rid of u. I'm going to bring the negative 4 out front. So we have negative 4 cosine of u. What's u? Well, look at what we have. We have cosine of u. Cosine of 4x. So I brought the negative 4 out front. Cosine of u is that. And then we still have this sine of 4x. So one like that, and you could have one where you need a chain rule inside a chain rule, as we did for du dx up there. And now let's look at part L. We have 7 to something. I'm just going to write it up here. Y equals 7 to the x squared minus 3x. Oh, all of my fun noodle fragments are falling out. That was a lot of words that started with that. Fortunately, I have more. So we have y equals this. Well, we know how to take derivative of 7 to the u. So let's let u be that quantity up there. So maybe I'll just do it like this. So for part, what letter is this? L? Let u equal x squared minus 3x. Well, now, what do we have? Well, if u equals that, du dx is what? 2x minus 3. What's y? Y equals now 7 to the u. So dy dx, or sorry, dy du, well, we know how to take derivative of 7 to the u. It's 7 to the u log 7. From page 2, probably rule 3 on page 2 of the derivative rules. Well, now, dy dx just combines those two with multiplication. So we have 7 to the u log 7 times 2x minus 3. And we just want to get rid of that u now. So u is x squared minus 3x, so 7 x squared minus 3x log 7 times 2x minus 3. So all of these chain rule problems are important, and it's also good, even after you go through a substitution, it's good to see, it's good to compare the original function to your answer. So here, we have 7 to something. The derivative of 7 to something is 7 to something log 7. And then you multiply by derivative of the something. So I find chain rule very much easier to think about using inside-outside functions, using the word something. Because the derivative rules don't really tell us about many somethings. But they do tell us what happens if that something is just x. So definitely practice these computations. They're very, very important as we go through the semester. It's very important to have this process down. It's also important sometimes to jump straight from the original function to the answer. For one like this, it might be harder, but for other ones, like with the square root, it's convenient to get to that answer in one step for some of the things we do in Chapter 4.